All right, today we are diving deep into something that's absolutely central to our clean energy future, hydrogen combustion. And it's a fascinating story, really. It's about fire, it's about physics, and believe it or not, it's about finding a little bit of simplicity right in the middle of total chaos. So let's jump right in. You know, we hear it all the time. Hydrogen is this incredible zero-carbon wonder fuel. Burn it and all you get is water. Simple, right? Well, there's a huge catch. Hydrogen is just notoriously difficult to control. It burns incredibly fast, incredibly aggressively. So the question for engineers, the one that keeps them up at night, is how do we actually tame this wild beast of a flame so we can build safe and efficient engines? So to really get why the solution we're going to talk about is such a big deal, you first have to appreciate the problem. Let's take a closer look at what makes hydrogen such a tricky fuel to work with. Think about it like this. On one side, you've got your familiar fuels like natural gas. We've got decades of experience with them. We know how they behave. And on the other side, you've got hydrogen. It has a much faster flame speed and a wider flammability limit. And that means it can ignite in situations where other fuels just wouldn't, which makes it prone to some really dangerous stuff like flashback, where the flame can literally travel backward right into the engine's fuel system. Not good. And this really gets to the heart of the challenge. As the researchers in our source paper put it, the computer models we've spent years and years building for regular fuels, they're just not cutting it for hydrogen. They could be limited or maybe even totally useless. We're basically in brand new territory here, and we need a whole new playbook.
Okay, so that brings us right to the scientific mystery here. If we're ever going to build engines that can actually handle hydrogen, we have to be able to predict with real accuracy how its flames are going to behave when they get all churned up by turbulence. We've got to crack the flame speed code.
And the magic number that everyone is chasing is called the turbulent flame speed, or ST for short. Now, this isn't just some abstract thing for scientists to debate. This is the most important number for designing an engine. If your flame speed's too high, you risk that dangerous flashback. If it's too low, the flame just blows out. You've got to nail it. It has to be just right. For decades, the way scientists tried to predict this was with these really complex charts called regime diagrams. The most famous one is the Borchy diagram, which is kind of like this giant, complicated map that tries to classify flames based on how intense the turbulence is and the size of the little turbulent whirlpools or eddies in the flow. And for a long time, the go-to measurement from this old toolkit was the Karlovitz number, or K. Basically, what it does is it compares how fast the flame's chemistry happens to how fast the tiniest, fastest spinning little eddies are moving. The thinking was, if we know K, we know everything we need to know. But here is where the plot really thickened. When researchers ran their simulations, they found this really bizarre trend. As the Karlovitz number went up, the flame speed also went up. Okay, makes sense. But then it dropped, and then it went up again. This was a huge red flag. It told them pretty clearly that the Karlovitz number couldn't be the whole story. Something else was pulling the strings. And this right here is where the research gives us this incredible breakthrough. After all of that complexity, all those diagrams and confusing numbers, the answer turned out to be, well, surprisingly simple. So if it's not the tiny, chaotic, fast-spinning eddies that are in charge, what is it? What really dictates how fast that flame moves? Get this, it's the size of the biggest eddies. That's it. The largest, most energy-packed whirlpools in the gas flow are what truly drive the overall speed of the flame. It's that simple. And the data just makes this relationship unbelievably clear. The turbulent flame speed, ST, it goes up in almost perfect proportion to the size of the biggest eddies, a property scientists call the integral length scale. So, bigger main whirlpools of gas means a faster flame. It's this beautifully clean, straight-line relationship. The authors just say it perfectly here. By realizing that it's the big picture, the macroscopic structure of the flow, and not all the microscopic chaos that really matters, they found the key. I mean, this insight simplifies the problem in a massive way. It completely changes the game for how we can build predictive models. But why? Why is this the case? I mean, it's a great discovery, but to really understand it, we need to zoom way in and look at the secret structure of the flame itself.
We need to go from the what to the why.
So it helps to think about two different kinds of speed. You've got the global speed, that's our ST, the big picture burning rate that we now know is controlled by those large eddies. But then, if you could zoom all the way in to the very edge of the flame, you'd see a local speed, SD. And that speed is affected by all the tiny stretches and curves that the turbulence creates.
So you might be thinking, does this new discovery just throw out that classic flamelet idea? The theory that a turbulent flame is really just a nice, smooth flame that's been all wrinkled up? Well, surprisingly, no. The research shows this idea actually works remarkably well for predicting the big stuff, the main chemicals like hydrogen, oxygen, and water. The catch is that it's not quite as good for predicting the really reactive, short-lived chemicals called radicals.
And this brings us to what might be the coolest part of this whole thing. Even when you crank up the turbulence to insane levels, we're talking Karlovitz numbers over 1,000, the core reaction zone of the flame stays mostly intact. Those tiny little eddies that everyone thought would just shred the flame to pieces, they actually fizzle out. Why? Well, the intense heat from the flame causes the gas to expand so fast that it literally smooths out the smallest wrinkles. The flame protects itself. How cool is that?
So, okay, that's some amazing science. But what does it all mean in the real world? What's the payoff? Well, it's huge. It lets us build much, much better virtual engines. And here's why this is so absolutely critical. Building and testing just one single physical engine prototype can cost millions of dollars and take months. But a virtual one, running on a supercomputer, it lets engineers test thousands of different designs for a tiny fraction of the cost and time. It's how you accelerate innovation big time.
So now you can see this really clear pathway from a scientific discovery to a real-world solution. It all starts with discovering the fundamental physics, just like this. Then you take that new knowledge and you build it into more accurate computer code. And with that better code, you can simulate and perfect new designs on a computer, long before you ever have to build anything in the real world.
This is the bottom line right here. This new understanding lets engineers create way more accurate simulation models, the kinds of tools they use every day, like RANs and LES. By letting us focus the computer's power on what we now know truly matters, those big eddies, we can design safer, more efficient hydrogen engines, and we can do it faster than ever before. So let's just boil it all down. We've gone from this incredibly complex, confusing picture of hydrogen flames to something that's actually beautifully simple. By focusing on the largest whirlpools of gas instead of getting lost in all the microscopic chaos, we finally have a reliable, practical way to predict and ultimately control the awesome power of hydrogen. But the work is never really done. This research gives us an incredible toolkit for understanding hydrogen flames at normal pressures. But real engines, future engines, they operate at unbelievably high pressures, where the physics might change all over again. So the final question is, can our models keep up as we push into these new extreme environments? That is the next frontier.